Tom and I just threw these names up without any definitions, and the reviewing board came back and said, well, why do you define them? These are storage people. So the things that we're going to talk about are MRAM, which is magnetic RAM, and you've heard a lot about that from the last panel. Resistive RAM, which Sony was talking about, Amigo from Sony, and that works on a different mechanism. It's got a resistor that controls the current. It's either a low current or a high current, depending on the resistance. Well, MRAM kind of does that too. If it's magnetized, then it's a low resistance. If it's magnetized the other way, then it's a high resistance. And then you've got phase change memory, and that's the basis for the Intel Micron cross-point memory, which is used in Intel's Optane products and Micron's Quantix. And phase change memory is based on a glass, which if it's frozen quickly, then it crystallizes. If it's frozen slowly, then it comes, or it's the other way around. Yeah, if it's frozen slowly, it crystallizes. If it's frozen quickly, then it's in an amorphous state. The amorphous state doesn't conduct, and the crystalline state does, so that's also a resistive RAM. And then you've got a ferroelectric RAM, which is, Tom will describe what the mechanism is behind that. But you've also got a number of other technologies that we're not talking about. What's really cool about it is that they're all what chip guys, and I'm a chip guy, call a non-volatile memory. But here we say persistent, that they all hang on to the data that's written into them. And so Tom and I go to an awful lot of trade shows, and I went to IED, well, both of us went to IEDM, and we found out that there's been nothing done to really consolidate the field. We still have MRAM, PCM, resistive RAM, and FRAM all in big numbers at that show. The first big application for these is still unclear. Will it be embedded NVM? That means the non-volatile memory that is now NOR flash inside of logic chips? Or will it actually do better in the near term as standalone memories, which is like what Everspin is shipping right now, and I gather Avalanche too. Will it replace embedded RAM eventually? Does SRAM stand to be threatened by this? And then where does it stand in neural networks? I'll talk about that in a little bit. But everybody likes to talk, like Kevin Connolly did, about the fact that there are going to be 125 humaguma bytes of memory or storage that are going to be needed sometime out in the future. There's Kevin, he's hiding now. But that amount of storage is supposed to drive a lot of this adoption. I don't think it will by itself. I think instead the virtues of the new kind of storage will. We also noticed that everybody had papers at IEDM talking about their emerging memory technologies, and there's a laundry list of the people who were there. But what was interesting too is that even though all of these technologies are vying to replace flash memory, there still were papers on flash memory talking about it. And so I'll show in the next slide what that is. And so I put together a little list. It just shows how many papers there were for each one of the memory technologies. And so there were 9 flash papers, 3 for RAM, that's DRAM and SRAM, MRAM 13, resistive RAM 17, FRAM, surprise, was 30. And why were there 30 for FRAM and 13 for MRAM? Well, it was because there was a session all about MRAM after the show was over, and so some of the papers got delayed into that. But also, FRAM has had a resurgence because it went from using what's considered a nasty material in semiconductor processing, which is lead, to using hafnium oxide, which is something that is used in logic processes all over the place. And so all of a sudden, everybody's paying attention, saying, hey, this is good stuff. And PCM was accounted for 9 papers, it's a much more limited thing, but neural networks were, that's kind of a cross with that. Neural networks were a part of this whole thing, and there were 25 neural network papers showing the interest in AI, which was in my first slide. So I say neural nets and FRAM take the prize for the number of papers. MRAM had its own conference, so they had 10 more presentations there. It brings its number up, but still not quite up as high as FRAM. Resistive RAM was well represented, and I was surprised at how much flash coverage there was. But Tom will talk about another show that he went to, a couple of shows after that.
Indeed, I will. So one was actually the IRDS, which, if those of you remember, the SEMI used to do the ITRS, if I remember right, which would be the semiconductor roadmap. Well, IEEE standards now has this activity. So I was able to go to IRDS and a bit of the rebooting computing conference. It was put on by the IEEE. So these are two events that are put on November 2018, which is also, I think it was, that was beginning of December that IED was. Yeah. And so the thing that's driving a lot of thinking right now is the end of the Moore's Law scaling that we've got so used to. I mean, this basically things getting, and a lot of that was driven by the shrinking lithography. And so lithographies aren't shrinking as much, although this last year we did see the introduction of EUV lithography being used by some companies and getting down to very tiny features. So 5 nanometer may not be out of the question for at least computing devices. But regardless of that, what the end of the thing that's been driving a lot of our electronics has allowed is new types of creativity in the way that we're processing data and the things we can do with it. And there's all sorts of things that have come out of that. Here's the names of some of these: approximate computing, where you don't get exact results and it's good enough. There's an adiabatic computing, which actually is related to quantum computing. It's relating some of the thermodynamic principles there. Neuromorphic computing. And what's really interesting about this is they're often using these emerging memory technologies to emulate a synapse, sort of the functions of the synapse in the brain. And if you think about that, that could lead into some of these things people are talking about, like in-memory processing or that sort of thing. We got the same technology for processing. It's also memory technology. You know, put them together. What have you got? Then there's quantum computing itself. And although I don't have a picture here at the CES show, in fact, IBM is just offering a quantum computer you can buy with a real nice shiny steel cryogenic tank for their Q system. So these things are coming to whatever extent they're coming to be reality. The other thing that is the rise of new architectures, and especially a lot more sort of a zoo or a Cambrian explosion of special purpose computing technologies that people are using. They're building devices that can be used for what they often call accelerators that can process things locally. Okay, and people have come out with, say, these computational storage is one of the results of that. But there's other things like RISC-V computing, which Western Digital and other companies have been involved in. So there's fascinating things going on right now in terms of not only all these storage memory technologies, but also computing technologies behind them. And so Jim and I did an emerging memory report. We promised we'd cover some of the things in the memory report in here. And so here's the topic we're going to talk about: why emerging memories are necessary, understanding bit selectors, the technologies, the process equipment requirements to make this stuff, because it's a little bit sort of added to the CMOS processes, emerging memory companies, and then forecasting emerging memories and where this stuff may grow. And if you're interested in this, we do have flyers on it. And with this, I'm going to be actually introducing Jim, I think, for the first part of here, why emerging memories are necessary. Oh, sorry, after this slide. First I do this, yes. This is our back and forth thing here. So the basic issue is that flash can't scale with process advances. They're sort of stymied. It gets really hard to go below 15 nanometer with conventional planar flash. So 3D is said to be not cost effective with CMOS logic process. Nor scaling stops with FinFET, although they are getting some pretty small FinFETs. But 28 nanometer smaller processes need something new. Low DRAM densities load down the memory bus, and AI is expensive on a von Neumann machine, rather. And again, these are all things that are driving us to think creatively about the way we do processing. So with that, I give you Jim.
Yay, I need the microphone. This is a slide that I've been using for so long, it's ancient. But it's a very simple concept, and that is it's memory costs per gigabyte or something like that, and this is just kind of a relative scale on a logarithmic scale, and how they go with process geometries. And so these nanometers down on the bottom, that's just process geometries, and so that's kind of an idealized idea about where costs would go. And NAND flash stopped scaling at 15 nanometers, planar NAND flash. And so this is represented by the knee and the curve for the red line. That red line, if you can't take the process down to 8 nanometers, 4 nanometers, 2 nanometers, then what that means is that no matter whether you're building anything else on that chip at those smaller process geometries, the cost of the NAND isn't going to go down when you scale it. Now, the black line represents some other technology that has a wafer cost that's twice as expensive to produce as NAND flash. And so it's always more expensive than, well, this was actually, I think, NOR flash when I put this together. But this is representing just that there's an added cost for an MRAM or for a PCM or something like that, that you're going to have a problem with the black line ever getting down to the same level as the red line because of the fact that his wafer is more expensive.
Kind of a dark horse.
Yeah, once you get to the point where the NAND flash bits no longer get smaller, and so you can't get any more of them on a wafer, but if the other technology can get more bits on a wafer, then you get a crossover where that 2 times cost difference between the 2 wafers does not offset the fact that the thing has more transistors per wafer. If you're getting 8 times as many transistors or 8 times as many gigabytes per wafer on something that only costs twice as much, then you're going to end up with a lower cost structure. And so this is why everybody has been pouring money into emerging memory technologies for the past 40 years, is simply because they've been saying that, they've been thinking that this is a way that they are going to be able to get past the end of scaling, which is something that everybody's known is going to come, but they've never been able to figure out exactly when it's coming because people keep inventing new ways to push it forward. So that's the thing that's really been fueling getting into it. But then, Tom mentioned also the big memory and putting large DRAMs in there. I decided I'd copy a news journal called The Register by Inventing Words. I don't know if any of you read The Register.
Yes, the Register.
Yes. But bigifying memory. And I put this through Google Translate this afternoon into Korean and then put it back out. And believe it or not, Google Translate changed it to enlarging. It really did seem to understand what I was trying to say.
That's spooky, man.
Yeah. Anyway, so one of the problems that you have on memory is the memory bus, which is represented by this bus signal. That's one line on your memory bus. And you put on one DRAM module, one DIMM, and you end up with a certain capacitance. That's your 8 gigabyte DIMM. Let's say you want to take this up to 128 gigabyte memory or something like that. Then you're going to end up needing 8 times as many DIMMs. That's going to be 8 times as much capacitance on the bus. That loads down the bus. It causes everything to slow down. And so because of that, there are these things that you heard about earlier today of people using an 8-socket server to do 2 sockets worth of work, just so you can be able to get more DRAM modules on there because you need to have the processors just do the job of pushing current down the signal line. So one of the beauties of what Intel and Micron are doing with their 3D crosspoint in the Optane modules and in the Quantix modules is that they're turning that back into a single capacitive load so that you can have only 2 slots being taken up by memory and still end up with that 128. I put gigabit, I meant gigabytes. but still, that you can have a very large memory on there. So that's one of the real beauties, is that you can have a very large memory without loading down the bus. And SNIA has made very important contributions to allowing this to happen, not only for that, but also with a persistent memory programming model. Another thing that Tom talked about was artificial intelligence. And artificial intelligence, a lot of people show this diagram, which is kind of like this. They usually draw resistors in there. I just decided I'd put things inside the circles that are R1, R2, R3. Mm-hmm. Something that this does is this is organized like a memory. It's not being used like a memory at all. You've got a series of voltages from a bunch of, optical sensors or something like that coming in on the sides. You've got resistors at every single one of these cross points on here. And they have different resistance levels. And their values times the voltages multiply by each other. And some of you in the back might not be able to see, but there's an equation at the bottom that just says that the voltage coming off the bottom of this vertical line is V1 times the reciprocal of R1 plus V2 times the reciprocal of R2, It's just a very simple polynomial equation. You get one of those polynomial equations for every single one of these columns here. And so with a 64 kilobit array, you get 256 sums of 256 multiplies each in a single cycle. Now this cycle is going to be really slow. You know, it might be 1 microsecond, it might be 10 microseconds, but how long does it take for a high-performance processor to do 256 sums of 256 multiplies? And it's a big chip. And so that's what's attractive about this, is that you can do all of this all at the same time. This is one of those things of, I put the question in, should SNIA participate in this? You know, it doesn't sound like a storage thing, but by golly, you got to back up the values in this. And I would imagine at some point or another, a bunch of people are going to be saying, well, I guess it is a storage problem. We're going to have to worry about that. But that's out in the future, so let's not talk about it right now. Let's instead put the onus on Tom.
Or is it?
Here.
All right, so let's go back to the rebooting computing. A big topic there was AI-type problems, but also graph problems, high communication computation ratios, also things like feature recognition, which works well with low precision, analog, or maybe even approximate computing to decide, you know, is this a dog, is it a horse, that kind of thing.
Which is like the last slide.
It's kind of last slide, yeah. As you were saying, can you do this? Well, actually, at the CES show, which I was just at a week and a half ago or something like that, and they actually announced this initially back, I think, November. There's an outfit called Gear Falcon that is based around here and also in Taiwan and China. And they had an AI chip, and they had two generations, or their prior generation product used SRAM for doing this matrix storage that Jim was talking about for the AI work. They substituted that with MRAM in order to, because the MRAM took up less space than SRAM, they're able to get more memory on the chip for a given die size. So they have like a 40 megabyte MRAM on this chip. This actually came out of TSMC. So they actually were demonstrating this at the CES show with plans of shipping products this year. So an example of using these new memories, in fact, for these AI applications, I thought that was very interesting. So now let's understand bit selectors, and with that, I will get you back to Jim.
Back to the Tom and Jim show.
There you go.
Yeah. So you know, how do bit selectors work? And I think it was a gentleman from Avalanche talked about bit selectors, and also the gentleman from Sony in the last panel. And I just love this quote. This was during the 3D XPoint rollout, the very first rollout that Intel and Micron had in July of 2015, where Scott DeBoer, who's a Micron fellow, said that the select device is a big issue. How do you combine it with a memory element? And he said, you can make resistive RAM out of an eggshell, but you can't scale that. Now, what he was talking about is you know, it's really cool. We talk about MRAM, we talk about ReRAM, we talk about Ferroelectrics, et cetera, et cetera, et cetera. But that's supposedly the easier part of the equation. Actually coming up with a select device is supposed to be considerably harder. And I haven't done either one of them, so it's easy for me to just be the armchair guy who says, yeah, that one's harder. But, you know, I'll take his word for it. But, you know, the thing that I find a lot of people stumbling over is why selector devices are problems. And so this is, once again, a representation of memory. The green dots are supposed to be things that conduct electricity. The red dots are things that don't conduct electricity. And in a memory, as opposed to this AI thing that I just showed you, in a memory you energize a single word line, and then if there's a conductor somewhere over the word line, then it should route the current onto the bit line where they cross. And voila, you have it. And something that I don't show in here, but I will, is that when that current goes out for the valid bit, the current also goes the other way on the bit line. That's, you know, normal kind of a thing. Now, if for some reason you don't have your selectors set up right, and it goes up to that green dot on the top, and it conducts, then it energizes another word line. So now you've got two word lines active at the same time. And so every green dot on that word line then sends out a sneak path bit, an invalid bit, out through the bit lines on the bottom. And so that's what the problem is with sneak paths. And that's why everybody needs to work so hard to produce selector devices that work. In today's MRAMs, the selector devices are transistors. And it's really easy to control a transistor. But the trouble is that a transistor makes the bit cell size twice as large as it would be if it just had a two-terminal selector. And so people are working very hard to do two-terminal selectors so that they can have what's called a cross-point memory and have something that's very small.
So let's talk a bit about some of these emerging memory technologies here. And we've heard a bit about it already in the session just before us. So MRAM, resistive RAM, phase change memories, cross-point memory is an example of that, ferroelectric memories, and then a whole bunch of other stuff. And Bill's out there, so he's one of them. So first of all, MRAM, we talked about it before. This basically is the spin tunnel torque, perpendicular spin tunnel torque structure. Here you've got a fixed layer, and you've got this free layer that can change its orientation. And basically, depending upon the orientation of those two layers, you've got this thin oxide layer in between them that can conduct either well or tunnel electrons really well or tunnel electrons not so well, and therefore it'll have a higher or lower amount of current or higher or lower resistance what it is. In fact, what's interesting about a lot of these technologies is that at heart, a lot of them are resistive technologies, a higher or low resistance state. So the bit then is set depending upon the orientation of that free layer. Okay, and you have a way of writing that and then be able to read it back. So that's basically the MRAM structure there. Resistive RAM, actually there's a few different ways in which people do that. The two most common ways anyway, besides eggshells, is conductive bridge, where you actually get little pieces of, essentially little pieces of metal that are formed inside, they can go in and out of the solution, and they can then cause you to have higher or lower resistance in the path. The other one is oxygen vacancy, where either there's oxygen-rich and oxygen-poor regions, and that can change, changing the amount of that in the material will change its resistivity. So you have a top electrode and a bottom electrode, and the stuff in between, which either essentially changes resistance depending upon the currents and voltages you apply to it. The phase change memory, Jim talked about that before. You've got a material that, depending upon how fast you heat it up, it could how slowly you cool it down, or how fast you cool it down. It can end up either in a crystalline state, which is higher conductivity, or an amorphous state, which is a lower conductivity, and so you can create a volume of material in these chalcogenide materials here that, with a heater, that can, again, be either conductive or amorphous, and therefore changing its resistance. And then the ferroelectric RAM, which, and some of these technologies have had little niche products out there for a long time. Ferroelectric RAM is one of those, and also some resistive RAM products that have been out a long time for very small, niche, tiny amount of storage or memory applications. So I know Jim wants me to show this. That's the central atom moving up and down. You got it? Okay. So basically what's happening here, though, is that...
Wait a minute. Oh. Look at that. Look at that. The judges have spoken. You got a 10, Tom.
We got a 10.
Jenny, would you please show that to the crowd? It's the Olympic cycle. We got a 10 in the Olympic cycle. Okay, thank you.
Thank you.
Yeah, congratulations.
So basically what happens here... Thank you, Jim. What happens here is that there's an electrical polarization by, you apply a voltage... You apply a voltage to this thing, and you can get a polarization of this material. It actually has hysteretic properties, kind of like a magnetic material, only it's this electric polarization that you're changing. So that can be used, like with magnetic materials, that hysteresis allows you to have, two-state materials, and therefore, again, giving you a memory technology. So with that, here's a variety of these other technologies. We've got carbon nanotubes. Graphene memories, conductive electron RAM, polymeric ferroelectrics, ferroelectric tunnel junctions, ferroelectric FETs, interfacial phase change memory, TRAM, magnetoelectric RAM, which is MRAM, racetrack memory, which you don't hear much of anymore, but it's kind of a cool thing. And then let's talk a bit about some of the process equipment requirements to make this stuff. Now, all these memories are built between metal layers, okay? Now, the example I'm showing here is making MRAM, but these processes with some modification of what you're doing, sort of similar, whether it be MRAM or phase change memory or resistive RAM. So you've got ways in which you start off with the CMOS, your basic transistor logic, and then you have ways you deposit the materials on top of that. In the case of an MRAM, you have to anneal this stuff to create the right magnetic states. Then you do your masking patterning. Also in the case of MRAM, you do this ion beam etching, which you may not do in other technologies. Then, of course, you have to test and you have to make a chip out of the thing. You have to encapsulate it or have it be part of an embedded device. So those some of the ways these things are done. And let's talk a bit about some of the memory companies here. And this was supposed to be yours, I think, wasn't it?
You can do it.
I'll do this one, okay. So here's some of so there's a lot of technology developers, chip makers, equipment makers. We've got a huge list here, which I'm not going to go through.
But it's in alphabetical order.
But we did put it in alphabetical order, so you can take a look at that. And then let's talk about some of the results we had in the report. We looked, we're looking at these different memories and where they might be going.
I can talk about this.
You want to do this one?
Yeah.
Okay. There you go. You finish up, Jim.
Oh, well, no, I'll turn it back over to you when it comes to the chart.
That's
But this is just kind of the thing, this is the vision that drove the forecast that Tom and I put together for emerging memory technologies, is we decided that there was probably going to be a relatively slow transition for embedded memories. This is the memories that go inside logic chips that are built typically in foundries. And these things are built over a wide range of process geometries. And so, it would be, logic would be building at, 350 nanometers all the way down to 22 nanometers. And at the 28 and 22 nanometer nodes, it looks like most people are going to be using something other than NOR flash for their embedded memory. And so we see a very slow transition as these process technologies migrate. But it will be an earlier onset of this transition. For NAND flash, we think that there's an awful lot of inertia to keep going with the NAND flash technologies that we already have. And so there will be a transition sometime later on, probably the middle of this coming decade, for NAND flash to convert to something else once it gets past 500 layers, if 500 really is the maximum number of layers that people can do in 3D NAND. And then right now the thinking is that ReRAM might be a good candidate for replacing that, although that could change over this time. DRAM, we see something similar going on with that. There are a lot of high K dielectric materials that have not been used for DRAM yet that could be used in the future, and so it could have a later transition over to an emerging technology. Today, a lot of companies think that MRAM, because of its speed and because of the fact that it scales in a similar size to DRAM, that MRAM is likely to be the technology to replace DRAM. And both of those will take a lot less time to convert over than the logic. There'll be a very abrupt transition because that's what happens in these memory technologies is that they're, I only got a 5.
He got a 5.
The Olympic cycle has hit me badly. Okay. Well, anyway, so that's the vision that's driving this forecast. But things could change. This is kind of a long time period. But I don't want to talk about the numbers of the forecast. I want to stick Tom with that. So I'll give him the presentation.
Thank you again, Jim. That's all. So this is what we figured out from our report. And we're looking out actually based upon advice from one of the people we're working with. We stretched it out to 2028. And so we're saying, we looked at a high, medium, and low case of where this could go. And so, this is the chart here showing our high, medium, low, and the shipping capacities. And you can see that if we go to this normal case, or the median case, we could be out at something like 30 zettabytes of stuff shipping annually by 2028, according to the projection here. And also by that time, we figured that there's a good chance of something like a $6 billion market in one or more of these products by that point in time. So anyway, if you're interested more in that, we do have the report, and we got some slides in it. It's big, 160 pages, 111 figures, 31 tables, and you can buy that if you want or talk to us. So with that, questions? Do we call them out?
Amazing.
Nathan has a question. Who would have thunk?
Jim, early on you showed why it's hard for an existing technology to beat the cost characteristics, or a new one to beat the cost characteristics of an existing one. And you showed flash hitting that limitation on scaling and going flat. But that did not reflect the build-up that we see, the 3D flash. And doesn't that change the entire math for when things take over other things?
Yeah, that's a good question, and this was kind of a NOR flash slide, that NOR flash can't take advantage of the 3D structure. To do a 3D structure, you have to have a NAND string. So DRAM can't do it, SRAM can't do it. That 3D structure only works with a NAND type string. And so 3D NAND has gotten past that. And so now the thing that is limiting 3D NAND is going to be how many layers you can put up.
And where do you think that runs out of steam?
I listen to people rather than trying to second guess them, because I'm not anywhere near as smart as the people who are putting together all of these new technologies. And a few years ago, they were saying 32 layers. More recently, when Hynix disclosed to me, I think at the Flash Memory Summit 2016, that string stacking existed, then they said that 100 layers might be a limit. Now, even Samsung in their, they had a Samsung Tech Day, and they were talking about 500 plus layers, and I know that other companies talked about that. And so, I could probably plot a chart as to what year it was and how many layers people said was the limit. And you'd just extrapolate that chart and say, oh yeah, it'll be 50,000 layers by 2030.
And there's so many layers that you push them over with your finger.
I really don't have any idea where it's going to stop, nor what is going to cause it to stop. It's been a problem where people have said, well, we can't really build it that way, and then they find a way around that problem, just like everything else in semiconductors.
Just like everything else. But doesn't that really make it even harder for all of these other technologies that want to overtake flash because of that ability for the flash to build up? The others don't seem to have that.
It does do that. It extends the amount of R&D dollars that have to be thrown at the other technologies for them to be able to make it the big market. But you look at companies, some of these companies are saying, we don't want to take over NAND flash, we don't want to take over DRAM, but there's a niche that we can go into really well. And they're doing a good job of that. That might be all they do.
So, the future of a current technology is more of that technology often, right? And there's a lot of old technologies that are still being used. Heck, we're still using magnetic tape, So, and even the older planar processes, I was talking to people at the CES who are making this stuff, or SLC chips for special purpose applications. So, the volume of how much you use may go down and may change in terms of the way it's used. But if anything, we're ending up with more alternatives, not less.
Yeah.
All right, very good.
Need some
Thank
education.
you, Tom and Jim.